Last class we stopped at discussing acidic character when it comes to the CH2 groups, which you call it as methylene groups, right? And we learned that A is greater than B is greater than C greater than D here. Next one is about uh, ammonium ions, NH3 plus. Okay, so when you have these ammonium ions, they have been derived from base like RNH2 if you have it like a amine. If it takes H plus, we shall get this as RNH3 plus. Now, the acidic character of this depends upon the basic character of this. Or I can say, if this is a acid has to be unstable. This has to be unstable. If this has to be unstable, that means this ammonia should be weaker base. A weaker base generate a stronger acid here. Now, how do we notice that they are unstable in this case? So check it out. What would happen in these cases? If the acidic strength has to be more, definitely you will look into the cases whichever of the possible is unstable. Now, unstable comes from a weaker base. You remove this H plus, you will get a lone pair. Lone pair is delocalized in all three positions in this case, which means the lone pair is hardly available, makes it a weaker base. Since it is a weaker base comparative to others, it would produce a more unstable acid, which means it is highly acidic. So this removing H plus would be much easier being acidic. Therefore, if you notice, this is how the acidic strength will vary. Okay. So you got to check out based on the, instability of the conjugate acid. Next one. If you compare an amide forms here, right? Generally, if you notice an amide form, in amides, removing this H plus is easier because the negative charge that comes on nitrogen can push into resonance and it happens on both the directions. Here also the resonance could be observed on both the directions. And since benzene is a withdrawing group here, correct? Sorry, benzene is the one which will also give a resonance energy here as a plus M effect. So you can see this lone pair resonance and this lone pair resonance are clashing with each other. While that kind of a clash is not observed in this case, therefore we can say the second one is relatively more acidic than the first one. And here also, if you notice, in this straight chain, this methyl is donating, this methyl is donating. While here, these two methyls are not donating because one group is withdrawing with respect to the other. Therefore, again, the second one is more acidic than the third one. So if I have this as A, B, C, then the acidic strength would be B greater than C greater than A. Clear? You got to notice on the basis of what effects they are offering. Here, benzene offers plus M towards C double bond O, disrupting the resonance from nitrogen. That's why it is less acidic. Okay. While here, when lone pair is going on, this group is kind of withdrawing towards it. Since it is withdrawing, the resonance will be much more effective. Hence, removing this H plus is not that a challenge part. Next one. If you notice removing this H plus, you will get a minus charge that will be localized. While here the negative charge, which is conjugate base, will be delocalized. And here the negative charge is so much delocalized that it will be a part of an aromatic system, isn't it? So that will become a part of aromatic system. Hence, if you compare the acidic strength, this is how it will vary. In fact, if you compare the pK values, this is around 48, this is 44, and this is 16. So you can see the drastic change in the acidic strength due to aromaticity. Due to aromaticity. Okay. Next one. Removing H plus from here, getting a minus charge will make this ring aromatic. That's what we just learned. But removing this H plus, getting a negative charge here, makes this ring anti-aromatic. So it is very difficult to remove this H plus. Hence, it is very, very less basic. In fact, if you compare the pK values, this is 16 while this is 50. That clearly shows that removing that H plus is very challenging part. Okay. Next one. This is vitamin C. Vitamin C is ascorbic acid. Ascorbic acid has four different OH groups here. Now notice that every OH group, if you compare the first OH group, which I am writing here, the first one being like this. Imagine if I get H plus removed from here, then you will notice that there is a extended conjugation that is observed. Because the conjugate base is relatively stable, that means this H plus removal is easy. So it is more acidic. While in the second case, if you notice, if I get an O minus here, double bond O and OH, then here there is some resonance, not highly extended, but there is still some resonance. So we can say that Y definitely is more acidic than Z. Next, if you compare the next oxygens here, if at all I put it as O minus, okay, O minus, here it is withdrawing group, correct? And here also it is withdrawing group overall. So some amount of basic character can be developed on this one, okay, but it is still localized. While the last case, if you notice here, if you have O minus, there is only one withdrawing group on this end. So it is not highly acidic as such. So therefore, Y, Z, then P and X. So that should be the acidic character. P has more minus I effect. Here it has more minus I. Here it has less minus I effect. That's the only difference you will find. Okay. Otherwise, these two has resonance energy. Clear with this case? Ascorbic acid. The last one is called squaric acid. Here, in case if I remove this H plus, I will get a minus charge on it. And that minus charge can be pushed into resonance. That is, if I push it here, the existing double bond, which is there like this, correct? Double bond here and double bond here. So this group will try to push it here and minus charge will come here. Therefore, you will get a double bond here, O minus, this double bond and OH remains the same. Likewise, I can keep on pushing this pi electrons to the other side also. Okay. So between these two, you can see the minus charge has, pushed here. Correct. Now what I can do, I can make this O minus. So you can see this negative charge is moving all the way on this side. The resonance will only stop up to this point. But what if I remove this H plus also? That means it will also have a minus charge on it. So if that also has a minus charge, see the advantage. Now if this has a minus charge, this can move here, pi bond can move here, negative charge can come here. So which means you'll get negative here, double bond here, double bond here, double bond here, and negative charge here. This is the way the resonance works. And another way it can move here is that if you push this pi electrons here now, this pi bond can move here and this negative charge can go up. So you'll get minus here, double bond here, double bond O here, and double bond O here. Have you noticed something? The pi bond was here, now it is here, now it is here, and now it is here. That means it has completed the complete structure here, which is ring current structure. So if the ring current is completed, in case if the ring current is completed, what do we call it? That means this is one pi electron pair is present, which will lead to aromaticity. Hence, removing these two H plus will give you a very stable conjugate base. So 1, 2, 3, and 4, all four are equivalent resonating structures with aromatic ring. So these are all equivalent reso structures. They're all equivalent reso structures. That is 1, 2, 3, as well as 4. And most importantly, they all, because they are equivalent, they will be extremely stable. So if the conjugate base is stable, that makes the squaric acid very acidic. So squaric acid in a way is very strongly acidic, even though it appears to have OH group, it has strongly acidic nature. In fact, if you compare the pK1 value, that is removal of first H plus, it is 1.7, and removal of second H plus should not be very different as well, because it is attaining aromaticity. So it is 3.5. So which suggests that squaric acid is a strong acid, strong organic acid. Clear with this logic, everybody? Now, let us compare groups individually, functional groups individually on benzene. On benzene, if at all we have an OH group, we call it as phenol. And phenol has a pK value around 10. Okay. Now, by chance, if there are other groups on phenol like methyl at ortho, meta, and para position, and then you are comparing that with phenol, what will happen to the acidic character? Now, notice CH3 can offer mainly uh, you know, two types of effects. One is hyperconjugation, the other one is plus psi effect. Hyperconjugation is always observed at ortho and para, because just like resonance it is always observed at ortho and para. On meta, we will not consider hyperconjugation. Then plus psi is very high in the case of ortho, moderate at meta, and less at para, which clearly suggests that the ortho position is very strongly donating, electron donating group. So you can see here, if I check out the combined effect, it is strong electron donating group. While here it is electron donating group as well, not very strong though. Here also electron donating group, which is sufficiently strong. Okay, it is like this. This. Okay, if you compare the electron donating nature. Because at ortho position, the electron donating nature is the most, which means it should have the least acidic character. Because after removing H plus, it is the negative charge which will keep moving on the benzene ring. So anything that stabilizes the negative charge will be more acidic. And you know that only electron withdrawing groups will do that. While methyl is an electron donating group, so hence it will destabilize. Therefore, we can say hydrogen only, I mean, all hydrogens present on this phenyl ring. Okay, if there are only hydrogens present on this phenyl ring, that would be most acidic, then meta, then para, and the least one will be ortho, because that has most donating groups. Okay, I suppose the first case is clear. See the second case. When you have OCH3, OCH3 means oxygen contains two lone pairs on it. So that lone pair can push electrons and show plus M effect. Therefore, what are the effects you should look out for? OCH3 can offer plus M, and because of its oxygen connection, it can show minus I. And plus M is observed again on ortho and para. Meta does not consult with plus M hyperconjugation and so on. Minus I will be more effective when it comes to ortho position, then slightly less on meta position, and very less on para position. That leaves us that when it comes to plus M effect, plus M is extremely dominant over minus I. So that makes overall electron donating group. Meta is only electron withdrawing group because it is minus I. There is no plus M. While para is again electron donating group. Okay. Now, obviously, you can see here inductive effect is more. That means it will try to withdraw electrons. I mean, withdraw density to electron density towards itself. It will try to increase the acidic strength. While here it will try to decrease the acidic strength. Correct. So if minus I is more, we can say it has more amount of acidic character. And that's the only difference you can identify between ortho and para. Between ortho and para, definitely ortho has to be more acidic. Putting that into the picture here, we can say meta is the only one which is withdrawing, so that will be more acidic than H. Then between ortho and para, we find that ortho is greater than para. I guess this logic is clear. Next one is halogen. When halogen is present at ortho, meta, and para position. Interestingly, halogens offer plus M effect and minus I effect. Plus M effect again is observed at ortho and para. Meta does not involve any resonance. Minus I is observed very high on ortho, moderate on meta, and very less on para. This is based on the distance factor. And now, if you compare overall, you see that whenever it comes to halogens, the minus I is much dominant than their plus M. So you forget about what plus M minus M it is offering. You only emphasize on the inductive effect. So due to inductive effect here, all three are electron withdrawing groups. And you know that electron withdrawing groups, if they increase, acidic nature will increase. So between ortho meta para, definitely ortho, which is much closer to the O minus group, so that will be the most acidic. So ortho, then meta, then para, and last comes hydrogen. So keep in mind, when it comes to halogens, your comparison should be only on the basis of minus I. Next, NO2. In the case of NO2, it can offer minus M as well as minus I. If it's offering minus M at ortho position, you will see minus M is observed at ortho and para. Minus I is very high at ortho, then moderate at meta, and least at para. Overall, if you notice that in all three cases, it is strongly electron withdrawing group, and electron withdrawing group. These are all strongly electron withdrawing. Okay. So based on this, theoretically, it observes that ortho is mostly withdrawing, then para, then it comes to para, then meta and hydrogen. This is uh, theoretically expected. This is theoretically expected. But in reality, you will notice that para is slightly more acidic than ortho, meta, and hydrogen. Now, why this variation has come across? Okay. Now, this variation attributes to the hydrogen bonding that is being observed here. See, like this. You have O and H, and we have N, O minus, double bond O plus. This is nitro at ortho position. So, because of which you will see hydrogen and oxygen will have strong attraction between them. And due to this attraction, you can see 1, 2, 3, 4, 5, 6. A six-membered ring formation is observed. So now due to this attraction of hydrogen, it becomes challenging to remove this H plus away. That's why it will start showing intramolecular hydrogen bonding, which affects its acidic strength. That's why we expect that ortho should be more, but here para will be more. Okay. This is what happens to the acidic strength due to hydrogen bonding. So this one is actual. The first one is theoretical. That is what we expect, but in reality, this is what you'll get. And next, what if there are so many groups at, para position? You know that para will offer plus m as well as minus I. See, what are all the offers each group can give? Methyl can give hyperconjugation as well as plus I. OCH3 can give you plus m and minus I. OH also the same, plus m minus I. NO2 minus m minus I. This also minus m minus I. Chloride plus m minus I. NH3 plus m and minus I. Now you see methyl is electron donating group. OCH3 is also electron donating group. This is also electron donating group. This is strongly electron withdrawing group. This is also strong electron withdrawing group. This is as well electron withdrawing group because of minus I, but it is mildly withdrawing. And this is extremely strong donating group. Now you need to check out for acidic strength, withdrawing group will help. So which are withdrawing group? These three. These three should always come first. Within that, we know that NO2 has very high amount of minus I nature compared to cyanide or chloride. Therefore, you can see E is greater than F is greater than G. Okay. Then comes hydrogen. Nothing. Nothing is hydrogen. And which is A. I mean, nothing here means A, which I, because hydrogen I mentioned it as A. And then it is donating, which is mildly donating. The mildly donation group, out of these donation groups here, 1, 2, 3, 4. So CH3 is mildly donating, which in our case is B. And see, between OCH3 and OH, the minus I effect of OCH3 is much more than OH. Therefore, this is more withdrawing. Hence, we can say C is more acidic than D. And the least one will be H. Because amines will show very strong donating nature. Is this part clear? This is how you need to check out the acidic strength on phenolic form. Next, what if the same groups are present on the meta position? So in case of meta position, let's analyze the effects what they will give. In the case of effects, of course, this will not offer anything. B is offering hyperconjugation and plus I. Sorry, no hyperconjugation, my mistake. Because this time you notice that in the case of CH, this is at meta position. At meta position, you will not do hyperconjugation, inductive effect and all. So only plus I, this is minus I, minus I, minus I, minus I, minus I, and minus I. Okay. So if you compare the acidic strength here, you need to just compare which has the highest minus I amount. The highest minus I is for NO2. So that makes it E. That is greater than cyanide. That is greater than minus I group of chlorine. So which is G. Then between these two, if you compare the minus I group here, OCH3 has more minus I than OH. So which means C is greater than D. And then comes H. H has only minus I as well. And the last comes B, then A. Right? Sorry. First A, then B. Because B is in fact donating. Rest all are withdrawing. Okay. Hydrogen is neutral. So this should be the acidic strength. Please do check, everybody. So check out these two cases. If anybody has a doubt, They can ask, or if you haven't written, please check it out. Write it down. What is the order of acidic strength? See the next one, in case if you have only halogens in this case, check it out. Effect wise, hydrogen does not give anything. Fluorine offers plus M and minus I. Chlorine also does the same thing, plus M minus I, plus M minus I, plus M and minus I. You need to check out the overall effect here. So if you notice the overall, it is electron withdrawing group. But see, fluorine, it's kind of compensates sufficient plus I and sufficient minus I. Both of them are good enough. So strong donating as well as strong withdrawing. That's why the overall withdrawing nature of fluorine is lesser. So if you compare, iodine in fact has more withdrawing power compared to bromine, chlorine and fluorine overall. That's why if you compare the acidic strength in this case, correct. So this is the order you will find. So iodine, bromine, chlorine, fluorine, and last comes hydrogen. Okay, so this is the acidic strength. Everyone, make sure that you are aware of this terms.
So why is I greater than of iodine?
Well, you notice that when it comes to plus M effect on this position, see, iodine has to offer its lone pair here, correct? The orbital present here and here, if you compare, this is a 2p orbital, this is a 5p orbital, isn't it?
Mm.
Clear? 2p, 3p, 4p, 5p. So the overlapping of 2p and 5p are very weak, na beta. So it is not strongly donating with plus M, correct? While when it comes to fluorine, it is strongly donating because the overlapping is 2p and 2p. So in a way ये donate भी बहुत अच्छे से कर रहा है और withdraw भी बहुत अच्छे से कर रहा है because of its electronegative nature. So it is like it is getting nullified. The effects are getting nullified. अधिका clear बेटा? While iodine में donating power बहुत weak है, so overall withdrawing power will dominate.
आधा होता है, समझा।
Okay. And this always been followed on benzene ring. Okay, on benzene ring, whenever you see this is the same thing we will follow. Got it? Right. Next one. In case if they are at meta position, on meta position, the effects that they will offer, the effects that they'll offer is only minus I. This one will give you nothing, but all of them will give minus I. Because everything is minus I, it is electron withdrawing group by all of them. By all of them. And who strongly electron withdrawing group in this case? Fluorine, because based on minus I, fluorine जीतेगा हमेशा. So that means fluorine is greater than chlorine, then bromine, then iodine, and after that comes hydrogen. Okay, this should be the order. Notice next one. As it comes to these cases, when you have NO2 present at multiple locations, so one at ortho, second one is ortho para, third one is 2 ortho 1 para. It's pretty simple. More the number of NO2 groups you have, more is the withdrawing power, and more withdrawing power, more is the acidic strength. That's why picric acid is considered as one of the strongest acids. In fact, if you compare the pK values here, if you compare the pK values, phenol sits around 10. With one nitrogen, it comes around 7.8. With two nitrogens, it is around 4.5. With three nitrogens, it is around 1. So this is the range of acidic strength. This is the pK value. And that implies the acidic nature of these groups will be D very strong, then C, then B, then A. Okay. Now, here is one interesting thing that we should understand. See, the pK value of carbonic acid is around 6.2, correct? Which means if any acid which has pK value lower than 6.2, okay, then it will definitely react with HCO3 minus, gives away its H plus, and releases H2CO3. H2CO3 will always come out as H2O plus CO2. You will see carbon dioxide will undergo an effervescence of carbon dioxide, a bubbling of carbon dioxide is observed. When, what is the condition? Look into it once again. Whatever the carbonic acid which is forming, that should have a lower pK, higher pK value compared to the reacting acid. Okay. Now, from the phenolic structure, if you may have noticed, neither phenol is lesser than 6.2, neither 1-nitrophenol is lesser than 6.2. As long as you have 2-nitro, 3-nitro, they all can give this positive reaction. And that's what you will notice. So, because if you have at least 2 nitro groups at any position, their pK value will always be less than 5. Hence, they give positive, you know, hence, hence they can give brisk efflorescence, of carbon dioxide gas. Okay. This is a very standard JE question, asked multiple number of times. Check it out. Which of the following can give positive bicarbonate test? Just quickly try to recall the pK values, at least the range. You should be able to figure out that. If you know that, it becomes very, very easy. Everybody, check out. The pK value of HCl is -7. This is -9. This is 3. This is 10. HNO3, right? It is a strong acid. Again, it is -5. H2SO4, this is also around -6. HCOH, formic acid, around 3.8. This is 4.74. Benzoic acid is 4.18. Phenol is around 10. Phenol with 1 nitro, that comes around 7.5 with 1 nitro. With 2 nitro, definitely it is less than 5. Okay, here also it is less than 5. Here also it is less than 5. Here it is picric acid. Picric acid is 1. Sulfonic acid is -5. And we learned the squaric acid is, 1.75. 1.75. We learned the squaric acid pK earlier. Oxalic acid, okay, H2C2O4. Oxalic acid is around 2.5. Methanol is around 16. Acetylene is around 25. Correct. So these are the pK values of various acids. Sorry. So what I'm trying to tell you, everybody, remembering the range of different functional groups makes your life very easy to solve these questions. Got it? So please check it out. What is the range of various functional groups? Now, from here, it is pretty evident that which of them will give positive test and which will give negative test. So check out which of them can give positive test. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the 15. So these 15 acids can give positive bicarbonate test. Got it? Likewise, I can add it with any kind of groups. Let me tell you one more group before I give the complete list. What if I ask you, okay, directly a question where you have phenol and phenol is reacting with various groups. Suppose if at all I have a phenol at the center And this phenol is reacting with various ions, starting with OH minus. Then I have NH2 minus. I have H minus. We have Grignard's reagent RMgX. Then we have CN, sorry, Cl minus. I have uh, F minus. We have HSO4 minus. Then we are reacting with RCOO minus. Then we have RO minus. Then we have then we have R C triple bond C minus. Then we have R NH minus. Then we have R CH double bond C minus. CH double bond CH minus. Got it? And lastly, if you have ethanol, last one I forgot. Picric acid, yeah. No, no. Ammonia I have done. Yeah, only sodium. Yeah, sodium. Check. For these cases, what I would suggest, if you were knowing the pK values, check out. We know the pK value of phenol is around 10. 10 is the pK value. Now remember, if a reaction has to be successful, the product which will give an acid, product also will have one acid. That acid has to be pK value which is higher than the given pK value. So that means in any case which has a higher pK value will be a successful reaction. Okay. First, let us write the products. So in all of this, what are the products we can get? We will get this as H2O, NH3, H2. Sorry. Then we have alkane, RH, HCl, HF, H2SO4. Then we have here H2, half of H2. Here we have RCH double bond CH2, RNH2, RC triple bond CH, ROH, and RCO minus. This entire thing plus phenoxide is what you expect. Here also plus PHO minus is what you're expecting. So if you know what is the pK value of water, that should solve your question, correct? Let me tell you, the pK value of water is around 15.8. Ammonia is 38, H2 is 38, alkane ranges between 48 to 60, HCl is minus 7, HF is plus 3, H2SO4 is minus 6, sorry, minus 5. Next, here H2 is also 38, this is 44. Amines is also around 40s, and acetylene is around 25. Alcohol is around 18 to 20, and RCO minus will give RCOOH, which is between 4 to 5. All carboxylic acid will have around, sorry, not 4, 3. 3 to 5, between this range it will have. Okay. So if you compare this, which of them will be successful reactions out of this? Notice, first, let's start with this one. 15.8. 10 to 15.8, definitely successful. This one successful, successful. This is a successful reaction. This will not happen. This will not happen. This will not happen. This can happen, 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 and this will not happen. So these are the following reactions which are positive and which are negative. Okay. So I can use all these terminologies like phenol can give positive ammonia test. Phenol can give positive sodium metal test. Phenol can give positive methane test if the R minus is CH3. So that will give you CH4, which is methane test. Okay. If it is giving H2, we call it as, hydrogen gas test or a pop sound, which you can get. Next, acetylene test. That means HC triple bond CH. Acetylene gas can come. So acetylene test is positive. Amine test is positive. Correct. Alcohol test is also positive. Okay. This is the way you can compare any functional group keeping at the center and then compare whether those reactions are feasible or not. Now, what is that you need to know out of all of this is this one. So, as long as the pK values are clear to you, it becomes very, very easy. Got it? Now, if you ask my suggestion, this is one table we should always have in front of your desk and start watching multiple times that what are the pK values in general or the range for various cases. Okay. So this entire list of 25 various functional group acids must be known. Clear, everybody? Right. Now, a special case of acids include benzoic acid. Okay. Now, what's happening in benzoic acid? Let's see. Benzoic acid, if it offers to release H plus, you will get a benzoate ion, which is a carb anion. And within the carb anion, stability depends upon two factors. One, whether the benzene can push the electrons here and try to make a resonance. And second, phenol itself, phenyl as it is, have minus I nature, so it will show some minus I effect. But what has been observed that overall this resonance part will be slightly dominant over the withdrawing group. Hence, overall benzene group on COO minus is electron donating group. While if you compare the acetic acid, CH3 is a very strongly donating plus I group. Okay, and here the plus I group dominates over the overall donating group of benzene. The plus I of methyl in acetic acid, everybody, dominates over the overall electron donating nature of benzene. And that's the reason why, if you compare a benzoic acid versus acetic acid, benzoic acid is more acidic. This is more acidic. Now, in the case of formic acid, there is no effect only, there is no donating effect. Since there is no donating effect, definitely that is the most acidic. Hence, the acidic strength of these three, formic acid, acetic acid, and benzoic acid, varies this way. So, first one, formic, then benzoic, then acidic. Clear? You can notice the pK values also. Formic acid is around 3.8, benzoic acid is 4.18, and acetic acid is 4.76. Very close by values. Okay. So remember based on effects. Right, guys. Check out something carefully here. This pushing the electrons will destabilize an equivalent resonance which was already existing between C double bond O and O minus, correct? This CO2 minus has a very nice equivalent resonance which has been appearing, but benzene's resonance is disrupting it. Okay? Imagine a case by somehow we stop this resonance from happening. Benzene's resonance, that is benzene offering plus M. Imagine if I stop that. The minute you stop it, the equivalent resonance will be much more active. And what would happen to the acidic strength? Further increases. Which means if anyhow some groups being put onto the benzene so that this resonance is stopped, then the acidic strength automatically increases. And let me show you with some examples here. First, imagine I have a methyl group present on ortho, meta, and para position. Okay. Now, On the ortho position, suddenly the acidic strength is very high, which is very unlike case, reason being the hyperconjugation and both plus I, these are very highly effective here that should actually decrease the acidic strength. Okay, so the expected acidic strength should be hydrogen, then meta, then para, and least should be ortho. But what has been noticed is that the ortho has the highest form, the rest will follow the same order. Okay, now ortho, whether it is at second position, third position, fourth position, as long as we are talking about benzoic acid, any group present on ortho will make it most acidic. Is that clear? This is what we call it as ortho effect. That means any group present on the ortho position is making the benzoic acid making it highly acidic compared to others. Okay. And ortho effect should be applied only at two cases, everybody. One is benzoic acid, the other one is aniline. Now see, due to ortho effect, any ortho substituted group will always make it most acidic compared to other substitutions. How that ortho effect works, everybody? It works in two ways. One is SIR effect, that is called steric inhibition of resonance. The second is via intra-hydrogen bonding of the conjugate base. These two will offer, you know, uh, increasing acidic strength. Now, how does this happen? Let's see. When CO2 here, CO2 minus, and the benzene ring, all of them are on the same plane. So you see these orbitals, they are all showing some resonance and there are pi bonds present in them. And this carbon also has a orbital. Here there is a pi orbital. Here there is a pi orbital. Nicely, there is a resonance happening between them. Now, suddenly, what benzene does is benzene has a pi bond. It will push to offer a pi bond between these two carbons. And because these two carbons will try to participate, the resonance here, effective resonance, will stop. Now, that's where this bulky group comes into picture. Imagine if there is any bulky group, that means it is bulky, implies it is sufficient to repel this CO minus. If it can repel that CO minus, what will it happen? Have you noticed this is a single bond? Due to single bond, this carbon can rotate any direction. So that means it can keep on moving anywhere like this. So this is the bond. You can imagine my hand. This hand is the bond. And here we have C double bond O minus like this. Now, keeping this bond like this only, I can keep on moving like this, isn't it? So C double bond O minus, which was supposed to be planar like this, now it has turned this way. Why is that doing? Because this bulky group and this O minus or carbon, they will have more repulsions. The minute it will tilt around and try to become three-dimensional, correct? Then this orbital and this orbital does not remain parallel to each other. And you know that pi bonds can only be observed in parallel orbitals. Therefore, because it cannot be parallel orbital, this resonance is completely avoided. And if benzene does not participate in resonance, here the equivalent resonance will happen with a much higher magnitude. And who's responsible for this one? This bulky group. That means this bulky group should be the one which is giving SIR effect, steric inhibition of resonance. Okay, that's what I was trying to explain through this paragraph. Now, who all can give this SIR effect? All these bulky groups you can notice: methyl, ethyl, any alkyl, aldehyde, ketone, ester, acid chloride, sulfonic acid, acetic acid, SO2R, minus I, minus Br, NO2, NR2, NHR. All of these groups are the ones which will give SIR effect. Now, groups which does not offer SIR, the ones are very small in size, like cyanide, hydrogen, deuterium, OH, fluorine, chlorine. Only these are the ones which does not offer SIR effect. Okay, these are the one which will offer SIR effect. Now let's see one by one. If there is a methyl group, naturally it is donating towards benzene at ortho position, meta position as well as para position. And you know that most donating should be at ortho, correct? Expected, I'm writing the expected form. So because it should be most donating at ortho, that should be the least acidic. And then comes para, then meta, then hydrogen. This is expected order. But what is the actual order? Ortho will always be greater than rest of them. This is the actual order. Got it? Thus, you need to check out what is the expected order and what is the actual acidic order. Same logic, if you have NO2 here, NO2 will also offer SIR effect. So the expected one will be NO2 is extremely influential at ortho position. So at ortho position, it should be highest. Okay. Then comes para, then comes para, then comes meta, and last comes hydrogen. Now notice that whether you put it into ortho effect or not, even with the normal effects also, that means with plus M and minus M also, still ortho is more only. So here expected and actual matches correctly. Third case, if you have OCH3. In case of OCH3, the expected value will be OCH3 dominates with plus M on ortho position and same at para position. So only withdrawing power is at meta. So meta, then comes ortho, then comes para, then comes hydrogen. Sorry. These are donating. Meta, hydrogen, ortho, and para. This is what is expected. But what is that we need to do? In all the cases, only one thing. Pull the ortho at the first. So ortho should be greater than meta, then hydrogen, then para. That is the actual order. Okay. Next one with halogens. Halogens expected and actual are same again. Because when it comes to halogen, we should rely only on their inductive effect. So you know that inductive effect offers best at ortho position, meta, para, and then hydrogen. So this is the same order which is followed even, actually this is the same order which has been followed. Next, COOR. COR is very strongly withdrawing group here. And because of that, again at ortho it should be more, then para, then meta, then hydrogen. Next, phenyl. There is one more phenyl here. So this phenyl will offer, you know, minus I here. So therefore ortho, then para. Okay, sorry, para is donating, then meta, then para, and then hydrogen. This is the order which we need to check. And that is the same order because, logically also, by ortho effect also, you are getting O only. Now, the cases where ortho effect is actually due to intra-hydrogen bonding. See what happens here. In case if at ortho position I have OH group, okay, think about it carefully. If you have an OH group here, what should happen? We should get this as C, O, and H. And here we have O and H. O and H here like this. And here we should have double bond O. So definitely this oxygen and hydrogen can offer hydrogen bonding or vice versa also. That means it might happen like this, that this hydrogen is going here and H is here, and between these two there is a hydrogen bonding here like this originally. Okay. So if you have a hydrogen bonding here versus the same logic versus if I put a hydrogen bonding after removing the H plus, after removing the H plus, what would happen? Now you get a negative charge on it. Now, due to negative charge, the attraction will be even stronger. Between these two, you'll have even strong attractions. And because of that strong attractions, the hydrogen bonding is very strong. So that makes this compound more stable. And you know that if conjugate base is stable, it means its original acid is very strong acidic. That's the reason why at ortho position, it's not because of the crowding, but because of the stability due to the ring formation. And more the intra-edge bonding, more is the acidic strength. And again, that pulls you the same thing. More amount of ortho groups, more is the acidic strength. Okay. So that's clearly visible in the next case also. That is when it comes to the acidic strength here, you can clearly see that between these three, which is more acidic. So the one which has more number of OH groups on the ortho position. Same logic with methyl. This is due to SIR effect. Ortho is greater than normal methyl group and then only benzoic acid. And more the bulkiness increases, right? More is the difficulty for CO minus to make any resonance. Hence, the acidic character will only increase like this. Next, if you have fluorine, chlorine, bromine, and iodine, and now you have to check out which one is more acidic in this case. I told you that iodine on benzene is strongly withdrawing than bromine, then chlorine, then fluorine. Hence, the acidic strength will vary like this. This will be the acidic strength. Lastly, if you have different groups present on ortho position, that means सारे के सारे ortho effect दिखा रहे हैं, but if all of them are showing ortho, which of them is a better ortho or more ortho? That depends upon whether they are withdrawing or donating. You know that this chlorine is withdrawing, bromine is withdrawing, but OH is still donating. OCH3 is still donating. NO2 is withdrawing. Okay. Now, from this, we can say I can directly compare the pK values, everybody. See what has been noticed. The pK value of benzoic acid is 4.18. This is 2.94. This is 2.85, 2.98, and then 4.09, and lastly 2.17. These are all the forms which you have. So based on that, it is pretty much clear that NO2 is strongly withdrawing. So it has to have more acidic strength. Then comes bromine, then chlorine. And that should be the order, and it is following. So we can say if we compare the acidic strength here, so definitely, let me put this as A, B, sorry, here. This as A, B, C, D, E, and F. So F will be the highest one, okay, and most acidic one. Then comes, bromine, which is C. Then comes chlorine, which is B. And thereafter, we can see all of them are donating only, but they all have to be greater than benzoic acid. So that's why the next one is found to be D, and then E, and lastly A. So this is the acidic strength order. Please check. And last, in case if you have, three different COOH groups on this triphenylene position. In that case, notice that at position A, this ortho methyl is there, and this is even very, very bulkier. That means this COH has ortho effect from both the ends. While here COOH, of course, there is an ortho effect because of this big group here, but ortho effect is not as expected as that of A case. Then C does not have any ortho effect. So that makes it clear that A has to be more acidic than B than C. Okay, this is based on ortho effect. Next. Notice. Check out generally what is the pK value and how do we compare the uh, acidic strength of the ammonium salt. See, NH3 is an ammonia, and if it takes H plus, it will become ammonium salt, right? So this will become anilinium salt. This is pyridinium salt, salt ion. Now the pK value of ammonia is 38, NH4 is around 9, this is around 5.6, and this one is around 6. So from here it is very clear that as it comes to most uh, acidic value, correct? So the highest has been identified in this case as the third one. So A, B, C, D, if you compare, the acidic strength in this case implies C greater than D greater than uh, B greater than A. This should be the order. Next. In case if you have COOH, COH and one NH3 plus present, have you noticed that any carboxylic acid will have a range between 3 to 5, while ammonium has around 9. Okay. So ammonium should be the least one, and here COOH, which has more withdrawing group very close by, so that should be most acidic. So C, then A, then B. So this is about ammonium based acids. I guess that's clear, right? Now, have a general look of all the acids, which will come across: water, hydronium ion, and peroxide. Water is 15.5, hydronium ion is minus 1.7, peroxide is 11.2. So you know the acidic strength now. Next, cyanides and nitro groups. Okay. If there is one cyanide, the pK value is around 25. Two cyanides is 11, and three cyanides, makes the hydrogen very, very acidic. Next, in case if you have nitro, the same logic applies. The pK value is lesser, then it is 4, then it is minus 5. Next, check out in this case here, NO2, methyl and methyl, they will repel each other. Because of the repulsions here, this NO2 will go out of the plane. And when it goes out of the plane, no resonance. So it will only offer minus I effect in this case. NO2 only offers minus I. While here, cyanide is linear. And because it is linear, you know, uh, it would still show minus M and minus I. But nitro is only showing minus I. Therefore, if it comes to overall electron withdrawing nature, definitely cyanide part. This will be more acidic than this one. Next, in case if you have NO2 and cyanide here, so you can see in this case minus M is very dominant over minus I. Same goes to cyanide. But if you compare NO2 and cyanide, we usually give preference to NO2. But cyanide is also sufficiently acidic. All good? And see next. If it comes to minus I generally, which influences the acidic character, okay? So overall minus I effect, if you compare, this is the order you will get. CF3 is strongly withdrawing, then NO2, then cyanide, fluorine, chlorine, bromine, iodine, and phenol. Now that is a list which we have drawn it here. So you can see CF3 is strongly withdrawing, then CCl3, then two chlorines, then nitro, okay, then cyanide, then one fluorine, then one chlorine, bromine, formic acid, and then uh, this one. So we will have only COH, then benzoic acid. After that, we can get one CH2 in between. then acetic acid, and finally propanoic acid. This is given in NCRT second year, so you better start learning the order from now itself. Some more important cases, if you observe, see, we have a cis form here, and if you compare to that of trans form, cis form will make it more acidic. Okay, cis form will become more acidic. So they will give H plus more easily. We'll get CO minus, and CH3, you know, will start repelling this group here, correct? Making it less acidic. So that's why giving away H plus here, correct? This is like ortho effect only. Have you noticed that? What if I write a benzene ring here like this? Check. This is like ortho effect only. Okay. So in the case of trans, you will see that logic is not very much sufficient, because here methyl and COH are far away, right? So when it comes to acidic strength here, so we can see that cis is more than trans. Next, feasible reactions. What are all the feasible reactions? So you can see pK value is 10, the water value is 15.5. So yes, this is feasible. We just learned it already. When do we take this as feasible case? So everybody done with these cases? Right. So these are all the acidic cases which you need to know. Now let's enter into the basic character of organic compounds. Okay. Basic character is decided based upon its Lewis base characteristic. That means it should be able to give away lone pair. Okay. Another way to look at it is it should be able to accept H plus ions. Okay. So you can see if you have a B minus and base which is minus, if you add it to water, if it is taking H plus and releasing OH minus, that is what the equilibrium constant is, what we call it as Kb, and Kb is the ionization constant of base. So if the Kb value is more, which means the OH minus concentration is more, which means it is strongly uh, basic character. So which means the basic character is more here. Basic character is increasing. So you can notice that the Kb value increases, the pKb value decreases, and the basic strength increases. Okay, right. The other way of looking at it, suppose if you have a base BOH and it took H plus from water and it has become this conjugate acid. Now for this conjugate acid's stability also we can decide what is the Kb value. If this conjugate acid is very stable, which means Kb value is higher. So if Kb value is high, pKb value is less, and pK value will be more, but the basic character will be more as well. Is this case is clear? Now, what are the factors that affect the basic character in general? First, percentage S character, plus I minus I, plus M minus M, SIR effect, SIP effect. This is a new one, we'll discuss it. Then we have Brett's rule, then we have flipping. These are all the case studies. Check out one by one. Resonance. How resonance decides the basic character? Check. If there is a localized electron here, because this lone pair is not going in resonance anyway, that would still be more basic compared to the electrons which are delocalized. So localized versus delocalized. So the basic medium in this case will be the first one, and the second one, if you compare, the first one will be more basic than the second one. Okay, next. If you have C double bond O NH2, then I have this group and then I have NH2 here. So C double bond O will make a very strong resonance with the lone pair of nitrogen. Okay. So with nitrogen, we will have this as NH2 plus O minus, which means the lone pair is hardly available. You can see that's what I have written. Hardly lone pair is available. While here there is availability, but with some resonance. Here there is no resonance at all. So if I take this as A, B, and C, so we can see that as the basic medium, you will see C is more basic than B, then A. This is the order of basic medium. Sorry, basic nature. This also confirms the fact that amides are very, very weak bases. In fact, most of the time we take them as neutral part. Next case is about hybridization. See, do not bring the effects like plus M, minus M, inductive effect, all of them. When you are comparing two, three different groups here. For instance, I have this NH2, which is a different family, primary amine. This is imine family. This is nitrile family. All three are three different functional groups. Amines are at sp3, imines are at sp2, and cyanide is at sp. Okay. Now, only check on the basis of, you know, percentage S character. Here, percentage S character is more, so which makes it, uh, sorry, which makes it less basic. While here, this is completely localized and sp3 hybridized, so that makes it more basic. So, which means if you compare this as A, then B, then C. So, what do we get? We will get this as A, which is highest, and then B, then C. Sorry. Notice the next one. What if I compare an sp3 which has some resonance on it, and then there is sp2 which also has resonance with C double bond O, and then there is no resonance but it is sp hybridized. Then it is sp hybridized. In such case, what you will notice is the sp3 here is far more basic than amide, and amides are still more basic than nitriles. So this is the basic strength. Okay. So keep that in mind. The influence of hybridization is very high. So higher the hybridization, more is the basic character. And if you check out more with respect to percentage S character, so you can see more percentage S character, less is the basic character.
So,
Yes, Vita.
sir, in the C double bond O NH2, the sp2 hybridized one. Sir, how is the sp2 hybridized?
Well, the lone pair is always in resonance, and it is hardly observed that the nitrogen is having a lone pair at all. So it will always exist in this state. Although I'm writing it in this form, the actual existence here is always in this form, which makes it sp2
It does
hybridized.
stabilize. It becomes sp2 hybridized atom.
Yes, beta. Amides are the only form where they are completely sp2. Now you might wonder, sir, should I put the same logic on everywhere else? No, not so much. Why? Because when it comes to aniline, now here also this is giving resonance. So can I say
Yes,
this
sir.
will be sp2? Well, it will not be completely sp2. It will be between sp2 and sp3. Okay. While
Okay.
only in the case of amides, the complete transfer of electrons are observed and they have more sp2 nature than sp3. Okay, beta.
Okay, sir. Thank you, sir.
What is the next one? SIR effect. SIR effect is based upon if already there are some groups present in ortho position, and here we have two methyl groups or two ethyl groups or so, then you can see these two groups will strongly repel, these two groups will strongly repel. And if they repel, what will happen? The nitrogen will start tilting around. It will become perpendicular to benzene. Okay. So this nitrogen along with this alkyl group, they will become perpendicular to benzene. If it becomes perpendicular, now this lone pair is completely sp3, isn't it? Because now there is no uh, donation of electrons at all. So this is completely sp3. This will also be sp3. Here it will have some mixture of sp2 and sp3. So if you notice the percentage S character wise also, which one is more basic here? So if I take this as A, B, C, definitely A, B, and C. This is the order. Everyone clear? See the next example also. In this case, there is an SIR effect, but here there is no SIR effect because the same NO2 groups, if they are replaced towards meta position, now there is no SIR effect. Now this lone pair will be in resonance. So that will make it strong resonance towards itself. Hence, the lone pair is less available, makes this compound A and B, if I compare, then the basic character will be more for A than B. See the next one. If you compare all these cases, we have SIR effect here. Here we have SIR effect. Here we have only plus I. Here there is no effect. Now, this is last two are very different cases, everybody. The first four are cases, I mean, first two cases are SIR effect. Here it is only plus I, no plus I. So, which means I can clearly say that the first one is more basic than the second one, third one, and fourth one. But the aniline group here now will be more acidic than the next one as compared to the next one. The last two cases are the typical cases of ortho effect. And the name of this ortho effect when it comes to anilines, we call it as steric inhibition of protonation, SIP. So the ortho effect's name for aniline is SIP, steric inhibition of protonation. Okay. As I go ahead, I'll explain what is the ortho effect on this amines part. As of now, see the next case, Brett's rule. If there is a violation of any Brett's rule happening, see, in the first case, there is a lone pair on nitrogen, which can easily make a resonance here, like this. But in the second case, if it wants to make a resonance, the ring structure will not allow it because getting a double bond on a bridge position is impossible. Okay, so that double bond formation is not observed. Hence, the lone pair remains localized, while here this one becomes delocalized. Hence, which one is more basic here? Second one. Second one is more localized. So that will be the more basic case. Okay. Next one is aromaticity. Based on aromatic nature, we can discuss whether they are more acidic or more basic or not. Sorry. Notice the lone pair present on nitrogen can push the electron so easily. In fact, the nitrogen here, lone pair is hardly available. This nitrogen is completely sp2 hybridized. As it is, I discussed about amides. The same logic applies here also. So the lone pair on pyrrole is hardly available beta. So it makes it extremely, extremely weak base. Here there is a lone pair donation. So this will be somewhere between sp2 and sp3. And it is delocalized. This is delocalized. And this is highly delocalized. Okay. Third one, here also this is localized here. So this is localized. Got it? Because in pyridine, this lone pair is not participating anything. Now this lone pair, which is completely localized, and it is sp2 sp3 hybridized. So we have our winner that this sp3 nitrogen is the most basic one. Then this is still localized. This is better. Then this delocalized, and the most delocalized is the first one. Thus, the basic character should vary like this. This should be the basic character. Okay. Next one. You see, pyrrole is the one which is the weakest base of all of this. In fact, pyrrole, you know what happens if H plus has been added, instead of adding it on nitrogen because the lone pair is hardly available, it will attack on some pi bond. So pi bond will get added here instead. Okay. So that much weak base it will be. Now notice the case where there is only plus I minus I being applied. Now the first case is sp3. In fact, all of them are sp3. And notice from the side direction, these methyls are actually donating from both directions. While here, what happens is, this is sp3, lone pair is available. But from the other end, the nitrogen will start the second nitrogen will start pulling it. So that will decrease the basic character. So one thing you got to be clear in the mind is that if plus I and plus M increases, the basic character increases. And if there is minus I and minus M which increases, then the basic character decreases. So if we compare the basic character here, the lone pair present here and this way, if at all I have A, B and C, then you will notice that A is greater than B is greater than C. Why? Here oxygen is more strong withdrawing than nitrogen. See, do not see just because there are multiple lone pairs here, that means it is more basic. No, no. That's not the way we look into. We should look into the effects what they are causing. Second one, here also the same logic. In this case, nitrogen is being supported from all three directions via plus I. So this is all plus I. While here it is all minus I because one nitrogen will become a minus I to the other nitrogen. Hence the basic character, if I take this as A and B, definitely A is more basic than B. Okay. So this is based on plus I minus I cases. Now let's see if at all we have plus M and minus M. So the logic is still the same. That means any electron donating group are increasing and strength is increasing, then basic character will increase. Then basic character will increase. And if electron withdrawing groups are more, correct? So that will decrease the basic character. So if at all we have all these groups, NH2, OH, OCH3, NHCOCH3, we have learned them already, like which of them is strong donating and less donating or, withdrawing. So if I put that together, you will find the one which is strongly donating, correct? Strongly donating is NH2. NH2 is strongly donating. Then comes OH, which is strongly donating. Then OCH3. And thereafter, we'll have this as NHCOCH3, which is also donating. OCOCH3, strongly donating. Okay. And then comes methyl, which is donating. So up to this, they are all donating. Up to this, they are all donating. Then comes hydrogen, that means no group. And thereafter, we will have here NO2 came multiple times, only one time. Then we have chlorine, and the least one will be nitro. So that is the least basic form. So I guess the plus M minus M is clear. And same logic again with the other groups here. If you notice, OM is electron donating group, EDG. This is also electron donating group, electron donating group. This is electron withdrawing group very strongly, electron withdrawing group. So if I put the basic character here, so definitely you will notice that OH is very strongly donating, then OCH3, and then CH3. And then we have hydrogen here, then chlorine, then NO2, right? Sorry, then CCl3. Last comes nitro. That is the least donating case, or rather, it is highly withdrawing case. Next, you observe flipping of the ammonia groups. That means if there is an open chain like this, the nitrogen is expected to be sp3 hybridized. It is sp3 hybridized. It should be pyramidal in shape. Now, what happens? Nitrogen as a pyramid, if there are three groups present here, and then this lone pair is coming, and then there is one more nitrogen which is coming, moving in this direction. This is also moving in this direction. What would happen? You can see their lone pair will start clashing with each other. To minimize this repulsion, what will happen? Nitrogen, both the nitrogens will temporarily start making that orbital into unhybridized p orbital like this. Both of these nitrogens will start making into p orbital. Okay. Then that will try to minimize their repulsion, and then they will depart. After they collide, they will depart. Right. So this is the transition state which they will come across. Now this is planar. So you can see this is planar molecule here. This one is also planar molecule here. Now on this planar molecule, correct? What would happen? The lone pair will start slowly pushing outward here, or it can go inside here. Which means lone pair is not sticking to one orbital here. Lone pair is not sticking to one hybridized orbital. Lone pair is moving constantly within the p orbital. It is going upward lobe or lowerward lobe like this. So here the lone pair, although it appears like in a hybridized orbital, due to its movement as it gets repelled by the other ammonia groups, the lone pair will keep moving up and down like this in this lobe. So it is available, but not as good availability as when it is in a cyclic structure, because in cyclic structure, no flipping take place. Okay, because it is restricted already, it cannot become planar suddenly. Okay, so because it cannot become planar suddenly, it would have no flipping nature. Hence, if I compare this as A and B, basic nature B is greater than A. This is the flipping form. See the next one. The next one is about d orbital resonance. Okay, which is if you have nitrogen connected with three methyl groups. Okay, this is trialkyl amine. This is trialkyl amine. While here this is called trisilyl amine. Instead of methyl, now it is connected with silicon, so it is silyl amine. Now, one thing we are forgetting, that silicon, unlike carbon, has an empty d orbital. And because it has empty d orbital and it is directly connected to nitrogen, nitrogen has a lone pair on it. So that lone pair will immediately start supporting towards silicon. And this support, what we learned in chemical bonding, is called as back bonding. So you can see back bonding is offered by this nitrogen. Hence, it will not remain sp3. It will completely turn into sp2. So here lone pair is not available at all. So that makes it extremely weak basic. So if I compare A and B here, A is far, far more basic than B. Everybody clear with the d orbital resonance? Next. Effect of solvent. How the solvent affect the basic character. You see, if you have polar aprotic solvent or non-polar solvent, polar aprotic solvent, which are those? The ones which have polarity, but they do not have hydrogen, which is highly polarized, like ethers, like ketones, like sulfur group, like this. This is called as DMSO. These are called polar aprotic solvents. Then we have non-polar. What are non-polar means? Non-polar is like CS2. You can take benzene. We can take toluene, correct? We can have CCl4. These type of liquid solutions. These are all liquid solutions. These are called non-polar solutions. So in case if you have polar aprotic solutions or non-polar aprotic solutions, the basic nature is only decided on the basis of inductive effect. So if I have 3-degree amine, this is called 3-degree amine, 2-degree amine, 1-degree amine, and 0-degree, which means uh, ammonia. In that case, higher the uh, alkyl groups, more is the plus psi effect. More plus psi effect, which makes it more basic. So which one is more basic in this case? So here you can see, sorry, here you can see this is more basic than this one, than this one. Even in gaseous state also, if the amines are in gaseous state, all of these are in gaseous state, then also you should only apply plus psi. So based on plus psi, 3-degree is greater than 2-degree, then 1-degree, then ammonia. This is the order which you will notice if the solvents are polar aprotic or non-polar, or for that matter, it could be a gaseous state also. Next, in case if you have polar protic solvents means like water, it has highly polarized hydrogens, like alcohol, like acids. These are called polar protic solvents. So if I take these solvents and then you don't have to judge only on the basis of inductive effect. There is one more factor that comes into picture. It is called solvation. So it is the result of both inductive effect and solvation which describes the basic character. Let me show you how. For instance, if I take ammonia, add it to water, okay, the lone pair from here will be taken, H plus, and it will become NH4 plus. Now what happens, the minute it becomes NH4 plus, immediately 4 water molecules will surround it. Why? All these hydrogens will have sufficient positive charge on it, and immediately the oxygen present in the water, which has sufficient delta negative charge on it, it will make an attraction here. And due to this attraction here, the positive charge gets induced in all 4 hydrogens, and that in fact will get attracted with oxygen. And because of which the stability increases. Hence, if the solvation increases, the stability of conjugate acid increases. That means basic nature of the ammonia increases. Okay. So now we need to judge on the basis of how much solvation we are getting. More the solvation, more is the stability of the conjugate acid, and therefore we can say the basic character is more. Notice, suppose if you have CH3N, that is trimethyl amine. When you add it to water, you will get this compound. Now you see there is only one hydrogen present to make solvation. So here the solvation is weak, but have you noticed this methyl groups will offer strong plus psi effect? So which means solvation is getting compensated with plus psi. And this is what happens usually. The plus psi and solvations are always, opposite to each other. So plus psi is inversely proportional to solvation. So whenever there is more solvation, that means there is less plus psi effect. And whenever there is less solvation, that means there is more plus psi effect. So you need to check out the combined effect on the basis. So this combined effect, that is both acidic character, both the solvation as well as inductive effect, together if you put it into the picture, you will find this, that in polar protic solvents, 2-degree is found to be the most basic, then 1-degree, then 3-degree, then methyl. Now here, including both the effects, inductive effect as well as solvation, this is what is the order you will get. So, everywhere aqueous solution is mentioned. If water is mentioned, that means the order of this amines will be 2130. So remember it as a number 2130. Instead of methyl, if you have ethyl, then it will become, 2 degree, 3 degree, 1 degree, and 0 degree. So this will be the order which you will get. So it is 2310. So remember, with methyl it is 2130, with ethyl it is 2310. Overall, if you compare the basic character here, starting with 2 degree will be more in both cases. So you can see this is 2 degree ethyl, 2 degree methyl. Then 3 degree amine, ethyl, then 1 degree amine. Here we have 1 degree methyl, then 3 degree amine. And here CH2PH will be slightly withdrawing here, correct? But overall, still it has sufficient donating nature. So hence, this is more like benzyl form, okay, connected with NH2. Last, ammonia here, which I can write it as 0 degrees, correct? And last, phenyl, it has resonance. So you can see the lone pair will be in resonance with phenol. So that will be the least basic case. Everyone, this part is clear, beta? So how solvent affects, you need to understand that part. Now let's come to the last part of the amines here, which is SIP, ortho effect. What we learned in benzoic acid, everybody, is that in case if you have any group on ortho position, right? Any bulky group on ortho position or any hydrogen bonding making a group, that will increase the acidic strength. And it is exactly the converse when it comes to aniline. If at all any group is present on the ortho position, the basic nature is drastically decreased. So any group present on ortho will make it less basic compared to simple aniline. Okay. Why would this happen? See, what is the problem here is ammonia is resonance stabilized initially. But what is the problem here is there is a bulky group at ortho position. Now, if you put it in acidic medium, what is the idea we should think of? That lone pair present on nitrogen should consume this H plus and convert into conjugate acid. Okay. Well, it does. After it is doing, can you notice that NH3 plus has become even more bigger because it has an extra hydrogen on it? And now it has CH3 already existing. So what would happen? Between these two, there will be strong repulsions. This will be a van der Waal repulsions. And because of the strong repulsions, this group will be less stable. Okay. That means this nitrogen is very reluctant to accept H plus. So it knows the consequence that if it accepts H plus, uh, it has to bear a lot of repulsion from the other ortho group. That's why this nitrogen will be very hesitant to take H plus. And this hesitation is what we call it as steric inhibition of protonation. That means it is not ready to get protonated. And because it is not ready to take H plus, that means it is very, very weak base. I hope all of you understood what is ortho effect in the case of anilines. Yeah. In the case of anilines, you need to check that ortho position has the weakest amount of basic character. Okay. So now let's see what are all the cases we have. The first case. What if you have methyl? What is it offering at ortho position, meta position, and para position? The effects what it is offering. First one. Here it is offering SIP effect. Directly I'll write only one thing. I will not show plus M hyperconjugation. All of that is irrelevant because the minute if you have SIP, that means it is least basic. Then at meta position, it will offer plus I. On para position, it will offer hyperconjugation and plus I. So para is strongly donating compared to that of meta. But SIP will make it weakest of the base. Hence, if you compare the base, para is definitely greater than meta, then hydrogen, and last comes ortho. So check out ortho will always come at the end. Clear everybody? So this will be the basic character. Next one, if you have NO2, NO2 again at ortho position, I'll simply write it as it is showing SiP effect. Meta position, you know that it shows minus I. Para position, it shows minus M as well as minus I. So again, based on this, what we can say, all of them are withdrawing except for hydrogen. So hydrogen only, that means aniline is more basic as compared to that of meta, as compared to para, and the least will be ortho. Okay, least will be ortho. Okay. Next. And you can see more the bulkiness increases along the ortho position, less will be its basic character. So therefore, the first one is more basic, then second, then third, and fourth. And next one. Bulkier the group at ortho position, lesser is the basic character. So you can see OH3 at this ortho position here. If it becomes bulkier, it will have lesser basic character. That is what is ortho effect is, correct? Now notice one thing. These two are slightly exceptions. These two are slightly exceptions. Why? OH3 is definitely showing, see, at ortho position, meta position, para position. The effects, if you compare, what are the effects it is giving? Okay, let me remove this part first. Let me explain the effects first. The effects what they are offering is, at ortho position it is SiP which is being offered, meta position it is minus I, para position it is plus M and minus I. Definitely para should be given more chance and ortho should be the least ones. But problem here is, although at ortho position it is showing SiP, still the lone pair present on oxygen can give plus M also. So plus M is observed, but in a mild condition. So as a mild way, it is showing plus M also. Okay. And that plus M is only effective in these two cases. Everybody, only with OCH3 and OH that plus M is slightly observed. Okay. Therefore, keeping this into picture, now if you compare the basic character, definitely para is major because it is overall donating. Then comes hydrogen and then comes ortho because ortho will have slightly donating nature, and then comes meta. So ortho should have been at the end, but slightly because of its mild plus M effect. But overall SIP is only dominating. Okay, overall SIP dominating. That's why it is still away from hydrogen, but slightly better than meta. The same logic applies to the next case also. Here also we have SIP with plus M mild. So mild plus M effect is observed. And here it has minus I. Here it is plus M and minus I. And these cases, if you compare, so the basic case in this would be most for para, then hydrogen, then ortho, then meta. Only these two cases are exceptions, everybody. OCH3 and OH are the exceptions at ortho position. Done? Now, picture this. The last case is about guanidine case. Okay. Guanidines are comparatively the strongest nitrogenous bases in organic compounds. Right? What is it exactly? This structure, a carbon holding NH and other two sides it is holding NH2 and NH2. Now you notice clearly this lone pair is delocalized, this lone pair is delocalized like this, and this is the only one which is localized. So definitely this lone pair will be the one which will consume H plus and convert into this conjugate acid. You notice one thing about this conjugate acid. Suppose if the lone pair is making a resonance stabilization here, so you will get a double bond here and lone pair there. Now same way, and plus charge here, right? Same way, if I can say this lone pair is been pushed and this pi bond is been moved here, so I will get a double bond here with plus like this, and this is the product you will get. Have you noticed something? Structure 1, 2, 3 look exactly alike with each other. and those three are equivalent resonating structures. And you know that equivalent resonating structures are very, very stable form. Since this is very stable, if you know that conjugate acid is very stable, which means its referential base will be very strong. So guanidine is a very, very strong base. If one of the NH2 is being replaced with methyl, it is called amidine. And if you compare amidine, this will also have equivalent resonating structures, but only two of them. Here we have three resonating structures, but amidine will have only two resonating structures. And that makes guanidine as very strong base as compared to that of amidine. Here also you can see this is strong base. Guanidines are even stronger base compared to a very generic sp3 localized case. Even if it has sp3 localized case, the guanidines are far more basic compared to that of these cases. Is this logic clear, beta? Everybody? This is called guanidine cases. Now, theoretically, this is how much you need to know, everybody. Okay. As it comes to cases, right? As you start working on the questions, you will be able to figure out what are all the cases that you'll come across. Okay. Now, in the next class, I'll be discussing all the cases that are possible. Correct?